Now, you are welcome again to the course Manufacturing Processes 2. Now, we are continuing module 2, Mechanics of Machining. Now, under this module, our lecture today will deal with cutting temperature, sources of heat and temperature, causes of such temperature, effects, assessment and control of cutting temperature. Now, what are the contents today? The specific instructional objectives. This will enable the students to identify the causes of development of heat and temperature during machining. Then state the effects of cutting temperature on cutting tool and the workpiece, the product. Then determine the value of cutting temperature by analytical methods as well as experimental methods. Next, evaluate the roles of various machining parameters on the cutting temperature, because our aim will be to reduce the cutting temperature as far as possible. For that, we must know what parameters affect cutting temperature and how. And last is point out the general methods of controlling, that is reducing the cutting temperature. Now, first let us discuss with the sources of heat and causes of development of cutting temperature during machining. This is the orthogonal sectional view of a cutting process. This is the work material, this is the cutting tool and this is the chip flowing with a velocity Vf and the cutting velocity is Vc. Now, the sources are, the first is the primary deformation zone indicated by 1, where the plastic deformation takes place and the chip comes out and separate out from the workpiece in the form of chip and flows out. Here the mechanical energy expended for shear deformation is converted into heat. Next one is the chip tool interface, which is also called secondary deformation zone. Because of the rubbing and secondary shear, lot of heat is further developed in this zone called 2, secondary deformation zone. And at the flanks also heat is generated to some extent at the flanks. The tool and work interfaces, the two interfaces, principal flank and auxiliary flank. So, work tool flanks interfaces. So, these are the three sources from where the heat is generated, and because of that temperature develops, which is shared by the chip, tool and job. Now, this shows the apportionment of heat in chip, tool and job. When the heat is generated, how it is shared amongst the chip, tool and job. From the shear zone, primary deformation zone, here you can see the major amount of heat goes into the chip and a small amount goes into the job, because the chip is flowing at high speed. Now, at the secondary deformation zone, that is chip tool interface, that is rake surface of the tool, major amount of heat that is generated goes into the chip, because the chip is generally of ductile material and tool is thermally conductive material. So, heat goes into that, and cutting tools have got poor thermal conductivity. For that it receives lesser amount of heat, and the heat generated at the principal flank and auxiliary flank, that is shared between the tool and the job. Major portion goes into the job, which is thermally conductive, more thermally conductive and is a large sink. So, it absorbs more amount of heat. Now, this shows that, say for example, at a particular velocity, here this amount of heat, say 75% goes into the chip, this chip, and 10%, around 10% goes into the tool and around 15% into the job. Now, fortunately the major amount of heat goes into the chip, which is thrown out. Whether it is affected or damaged by the heat, it does not matter, because it is not utilized. It is also important to note that with the increase in cutting velocity, the chip shares the major amount of heat. So, the share of the chip gradually increases with the increase in cutting velocity. That is when you produce more and more productive or high metal removal rate, major amount of heat goes along with the chip and a small amount goes into the tool and a rest amount into the blank. So, this is favorable. Next is effects of high cutting temperature. The cutting temperature is usually high, may vary from say 500 degrees centigrade, it can go up to 1000 degrees centigrade. So, which is very detrimental. Mostly the effect of the temperature is detrimental, and in very few cases it can be favorable. Now, what are the detrimental effects on cutting tool, that is cutting edge? So, it has got detrimental effects on the cutting tool and workpiece. Now, first let us study the detrimental effects of the cutting temperature on cutting tool. Rapid tool wear that reduces the tool life. Now, what is it? Say this is the tool and the chip flows over it. Wear takes place, this is the rake surface where wear takes place, this material goes out and here also the material goes out. Now, the rate of wear of this cutting tool increases with the increase in cutting temperature. When the cutting temperature is high, this wear grows very fast and the tool becomes blunt in short time. So, it reduces tool life. Now, next is plastic deformation of the cutting tip. If the tool material, this means, suppose this is the sharp cutting tool. Due to high cutting temperature in this region, this portion, this is subject to high stress and high temperature, it can undergo plastic deformation like this. It can undergo plastic deformation like this also. Whatever be the amount or type of plastic deformation, the sharpness of the cutting tool is totally lost and the cutting tool becomes unable to cut and it breaks. Especially if the work material, if the tool material is not enough hot hard and hot strong. What is hot hard? A material may remain hard and ambient temperature, but it and strong, but it has to hold its strength and hardness even at high elevated cutting temperature. That is called hot hard and hot strong. The material of the cutting tool should be like that. Then thermal flaking and fracture. Now, what is it? This is the cutting tool and the chip flows over this. Sometime chunk of material gets removed in the form of flaking. So, this kind of material gets removed, particularly when the chip material sticks strongly on the rake surface. Then this kind, and sometime the fracture can also take place. This there can be fracture, like this, thermal fracture because of high thermal gradient. This can happen. And beside that, the built up edge formation. Built up edge formation, you know, at high temperature, at the chip tool, at the tool, the built up edge develops. Because of the built up edge, the cutting force increases, power consumption increases, and there can be breakage of the tool. So, a lot of problems arise. So, these are the detrimental effects of high cutting temperature on cutting tool. Now, let us go to the next. Detrimental effects of high cutting temperature on job. So, what about the detrimental effects on the product? Let us examine. Dimensional inaccuracy for thermal distortion and expansion contraction. Now, when a job is machined, suppose you are machining a rod, say turning. If we allow continuous heating of the job, then this can undergo some distortion, thermal distortion, and that will result dimensional inaccuracy. Beside that, when we machine, say when the cutting temperature is high, then we give a definite depth of cut, but after cooling the dimension will come down and the accuracy will be further lost due to contraction. Poor surface finish for built up edge. Now, poor surface finish because of built up edge and damage of the cutting edge. Now, what is it? Suppose this is the tool and this is the material flowing and built up edge is developing there. Okay. Now, when this built up edge grows further, it overflows and comes into the finish side, and then it forms some roughness on the surface. So, this overflown part of the built up edge remains stuck on the finished surface, and this causes roughness of the surface. Sometimes this can also cause the damage of the cutting edge. The cutting edge can be totally damaged because of this built up edge. So, this is a harmful effect on the workpiece, and if this cutting tool gets damaged, the job will be also damaged. What else it can do? The high cutting temperature on the workpiece, oxidation, burning, rapid corrosion, etc. Oxidation, burning, rapid corrosion, these are all spoil the surface integrity of the product. Induction of tensile residual stresses and surface and subsurface micro cracks. What happens? Due to high temperature at the cutting zone, at the cutting point, some residual stress develops, and you know that the residual stress that is induced by heat or temperature, that is tensile in nature, and tensile kind of residual stress is very harmful. Beside that, it produces, suppose this is the machine surface, on the machine surface there will be certain cracks develop like this. So, small cracks will develop on the surface, and even if the sometime if it is mirrored up, the crack remains inside. This is called subsurface cracks. Whether the outside cracks or subsurface cracks on a machine rod, suppose the machine rod is the machine surface, these are equally detrimental. That reduces the dynamic property and the fatigue strength of the material. So, these are all detrimental effects. Is there any favorable effect on this? Very rare. Favorable effect of high cutting temperature is very rare. Anyway, the possible favorable effect of high cutting temperature may be, here you see that we know the cutting force PJ, main cutting force PJ depends upon the depth of cut, feed, the shear strength of the work material under the cutting condition, and form factor. Now, this tau s, the dynamic yield shear strength of the work material, that gets reduced because of high temperature. The work material becomes soft, and softening means a reduction of the shear strength. If the shear strength is reduced, then the cutting force will come down, reduction in cutting forces, and because of that the power consumption, specific energy consumption all will decrease. This is a very rare favorable case. Now, it can happen especially when the work materials is very hard and strong, that is tau s is very high, very difficult to machine for that, and hardenable becomes harder along with the growth of machining. Because of this reason, this the possibility of reduction of tau s and resulting reduction of PZ, this possibility is often exploited in terms of what is called hot machining. What is hot machining? In hot machining, so this is the tool and this is the work chip coming out. Here the work material is deliberately heated from outside by flame or by friction or by say induction by eddy current. There are various methods. As a result, the work material, when it reaches this shear zone, the temperature rises because of there is some inherent cutting temperature because of shear deformation. Now, you are adding further heat, so temperature will rise further. Because of that, this tau s will decrease, and that will help reduction in the cutting force and power consumption, that is enable machining etc. Now, what are the applications? Machining of that kind of material which is very hard and becomes more hard during machining, like manganese steel, high manganese steel, hard, hat-fit steel, mnemonic, Inconel, and so on. So, this hot machining is often very useful, but this does not give very good surface finish or accuracy, but rough machining can be easily conducted by hot machining, and this is preferred for such kind of material. Now, the determination of cutting temperature. How will you determine the magnitude of cutting temperature and its distribution over the tool, chip, and so on? Before that, why should we measure? Why should we determine the cutting temperature? What is the use of it? Who will be benefited? Let us examine. purposes of knowing or determining cutting temperature. For assessment of machinability of any work material or tool work combination. Now, you know the machinability means ease of machining, which is judged by cutting force, cutting temperature, tool life and so on. That is cutting temperature. Lesser the cutting temperature, we call machinability is good. So, whether machinability is good or bad, for that we have to measure the temperature, know the temperature. So, this is called for assessment of machinability study. For design and selection of cutting tools, first let me tell about the selection. If the cutting temperature appears to be very high because of the work material hardness, strength and the cutting condition, velocity, etc., then we should take such a cutting tool material which can withstand high cutting temperature. That is, we should take say carbide cutting inserts instead of high speed steel. Beside that, the size and shape of the cutting tool, that is design, should also be taken care of for this cutting temperature to be reduced. Now, after design and selection, we should measure the temperature and study and decide whether design is appropriate or not. So, before design we must know the temperature and accordingly we should design, and after design we should measure the temperature again whether design is appropriate or not. Similarly, selection of the cutting tool. Next, to evaluate the role of variation of the different machining parameters. Now, we want to reduce the cutting temperature. Okay. Now, this cannot be done directly. This depends upon all the machining parameters and their values. What are the machining parameters? The process parameters, cutting velocity, feed and depth of cut. Tool parameters, material and tool geometry. Environmental parameters, the cutting fluid, etc. So, we have to study that what are the roles of these parameters on cutting temperature. For that, by varying these parameters, we must know either analytically or experimentally determine the cutting temperature. Next, for proper selection and application of cutting fluid, if we find that the cutting temperature is going to be very high, then cutting fluid has to be applied. If the temperature is very high, then appropriate cutting fluid has to be selected and employed, so that the cutting temperature, high cutting temperature can be taken care of, so that it does not damage the tool and job. It is also necessary to measure the temperature often for analysis of temperature distribution in tool chip and job. For study of the distribution of temperature in the chip, in the tool and the job, it is necessary for design of the tool, for analysis of the tool failure and all these things. For that, we must know initially what are the temperature at the different zones, like primary deformation zone, at the secondary deformation zone, at the flanks, what are the temperature. Based on that, the temperature within the chip, tool, job have to be evaluated by say computational methods like FEM or boundary elementary method and all these things. Next, let us find the basic two methods of measurement of cutting temperature. This is not measurement, actually this will be determination. Basic two methods of determination of cutting temperature, not measurement, determination. All right. There are two methods basically. One is analytical method by using equations, if available, if not available can be developed, and this will enable determination. This is process very easy, quick but inaccurate and not very precise. It gives generally average values, and though it can be done easily, quickly, but it is not accurate, so not reliable. But if you want very accurate measurement and distribution over the surfaces and locations, then experimental method has to be employed. These accurate methods are definitely accurate, more precise and gives detail, but may be difficult and expensive, because you have to use instruments, stop machinings, do some research work, and equipments, and expert people have to do work. So, it may be difficult as well as it may be expensive also, but this will give accuracy and precision of measurement. Now, when we talk about measurement or determination of cutting temperature, what we talk about, which temperature we are interested of? These are the average shear zone temperature. This is the shear zone temperature. In the shear zone temperature, what is the average temperature in this region? that is theta s. Then this is another major heat source, where at the chip tool interface there will be heat generation temperature, and average of that is theta I. At the flank, at the principal flank, suppose theta f, and sometime overall average temperature theta average. So, these are the temperatures which we are interested of for various purposes. Analytical estimation using developing equations, now there are various methods. Here it is interesting, should know that there are different methods, various methods available in the books and journals, and lot of people have done research earlier and developed lot of equations of varying accuracy level and reliability. But here we have got limited scope to discuss all of them. So, let us take one, say estimation of average value of shear zone temperature. What is shear zone temperature? This is the tool, chip is flowing, and this is the shear zone. What is the average temperature here? That is theta s. That is what we are going to estimate first. Now, this will be done by using this equation. So, what is this equation and where from it comes? Here you see that this is the tool flowing job, and the velocity is here, cutting velocity Vc. The force, main force is Pz. So, Pz into Vc, that is Pz into Vc, that is the amount of energy we are putting in for conducting machining work, that is utilized for causing shear, that is shear plane area multiplied by the shear area by the stress is the force, and this force Ps multiplied by the velocity in this direction, shear velocity Vs. So, this Pz into Vc should overcome or provide this amount of energy, and also to overcome the friction F and the velocity Vf. So, these two things have to be provided by Vc into Pz. So, Pz Vc is comprised of two parts. It has to provide this shear action and overcome friction at the chip tool interface. From this one, what is our interest is shear zone only at this moment. So, what is this energy? This energy is equal to Pz Vc minus Fbf. All right. So, this PSVS is the source of heat. Now, suppose this is the energy, mechanical energy here at the shear zone PSVS, and this is equal to Pz Vc minus F into Vf. We know Pz, we know Vc, we know friction force by dynamometer and the chip velocity from the chip reduction coefficient. So, PSVS is known. Now, whatever heat is generated here, so whatever mechanical energy expended here, a major part of that goes into heat. So, say fraction A. What is fraction A? Fraction A means amount of energy that is converted into heat. So, this is A. Say 95%. Around 95% of the mechanical energy, shear energy, will be converted into heat. After that, the heat that is generated in the shear zone, that will be shared. A major portion goes into the tool chip and a small amount goes into the job. Now, this apportionment, suppose heat is generated at this zone, and then a fraction, say Q is the fraction, maybe 70 to 90% will go into the chip and 10 to 20% go into the job. All right. Now, the chip which is coming out, the chip receives from the shear deformation this amount of mechanical energy multiplied by A and Q1. So, A into this one is the heat energy and Q1 is the fraction that goes into the chip, and 1 minus Q1 goes into the tool. So, this is the heat generated, that divided by J is the mechanical equivalent of heat. So, this is the amount of heat carried by, produced by and carried, absorbed by the chip due to shear deformation alone. Now, in 1 minute or per unit time, how much heat is contained by the chip in 1 minute if it comes out continuously? That is the cross section of the chip A1 B1, velocity of the so this is the amount of volume of the chip, flow rate of the chip that flows out, and this is the temperature, average temperature at this region, and this is the ambient temperature, and Cv is the volume specific heat. So, flow rate, volume specific heat multiplied by the difference in temperature. Just a minute, sorry. Sorry. Now, here what we find, this is the amount of energy received by the chip per unit time, and this is the amount of heat contained by the chip per unit time. So, now balancing these two, we get the equation, say A is known, say assume 0.95, Q1 is say 0.8, PS, Vs are known, J is known, Cv is the property of the chip material, A1, B1 are known. ठीक है, the shear energy, and theta A is the ambient temperature known. So, we have to determine theta S from this expression. Now, this is another analytical estimation of average value of the chip tool interface temperature. I remind you that this is the tool and this is the rake surface where the temperature is theta I. This has to be determined, the average value of theta I. How? One, there are many methods, very beautiful methods are available in different books, including A. Bhattacharya's book, Machining Theory and Principle. Now, using the Buckingham's, the starting point is using Buckingham's theorem, which states that there are two dimensionless quantity Q1 and Q2, two dimensionless parameters, and they are connected by a constant C1 and Q2 to the power n, where Q1 represents the volume specific heat of the chip material, theta I is the average temperature at the shear zone, at the chip to interface, and EC is the specific energy consumption, that is equal to cutting force Pz divided by unit chip area, chip cross section area, and Q2, this is given by this expression, this volume specific heat multiplied by the cutting velocity, process parameter, multiplied by the uncut chip thickness A1, which is equal to SO sin phi, that is phi and phi is the principal cutting angle, and lambda is the thermal conductivity whole square. Now, as I said, EC is specific cutting energy, which can be determined from the cutting force divided by the chip cross sectional area, chip load TSO, lambda thermal conductivity of chip, N, and index close to, this has been observed, studied experimentally and found that is very close to 0.25. C1 is a constant which depends upon the machining condition, that is the cutting fluid application, friction, sometimes tool geometry, and so on. Now, combining these three equations, what we get? Taking n is equal to this, n is equal to say 0.25, and then combining Q1 and Q2, we get an expression like this, very simple expression. Theta is equal to C1 is a constant like this, and EC is the specific energy consumed by the material, which depends upon the cutting force, etc., and then root over cutting velocity, feed, and thermal conductivity divided by thermal conductivity and this volume specific heat. So, if all these are known, we can determine theta I approximately, and this is average value, not at the point by point, only average value over the surface. Remember, the temperature at different points on the rake surface are different, all right. Now, so this what we have discussed, those are analytical estimation, all right. Now, we shall see how the measurement is possible. Measurement, experimental measurement or experimental determination of cutting temperature. Now, there are many methods which can be applied. Some of the methods are feasible, some of them are not that feasible, some methods are very accurate, some methods are not accurate, and so on. However, some feasible experimental methods which are normally used by the people who are interested in measurement of cutting temperature, they use these things. Say calorimetric method. Calorimetric method is a very simple, quick method, but definitely neither accurate nor reliable. It gives very average value, and for operations like drilling and so on, the heat is that is developed is contained in the water or the fluid, and from balancing we get the average temperature. Second method is also a crude method, but better than calorimetric, using decolorizing agent. That means, there are certain paints and chalks which, when pasted or painted on the hot surface, depending upon the temperature of the hot surface, the color changes. So, its color depending upon the temperature of the cutting tool or the job, the color of the chalk that is pasted or marked, or the paint that is marked on the tool or the job will keep on changing. And if you know in advance that what is the correlation between the color and the temperature, you can determine the level, at least the level of the temperature, not exactly from the range of the color approximately. Now, example, also cheap color. Now, for materials like steels, from the color of the cheap produced, the temperature of machining that was developed can be estimated, can be apprehended. For example, if the color of the chip is bright like steel, then temperature is definitely less than 500 centigrade. If it is pale yellow, then 600. If it is say orange color, 700. If it is brown, 750. If it is say chocolate color, 775. If it is a black, then it will be 800. If it is blue, then above 800, say 825, and it can be gray color, that is above 950 approximately. So, from the color of the chip of materials like steels, the cutting temperature can be estimated. These are not very reliable, these two are not very reliable, but what is reliable? These are very reliable. Say tool work thermocouple technique. This is a very simple method, very accurate, but it does not give the detail, but average value. Then moving thermocouple technique, embedded thermocouple technique, using compound tool indirectly from micro hardness distribution, photocell technique, and infrared methods. So many methods are there which can be used. Now, we shall discuss one by one those which are important. Say tool work thermocouple technique. In tool work thermocouple technique, here you see tool work thermocouple technique, the tool and the work will function as the two conductors of the two leads of the thermocouple. In thermocouple there are pair of materials, conductive, thermally electrically conductive materials, say copper and constantan, then chrome enamel, or different types of materials. The principle is, when these two metals are joined and the junctions are kept at different temperature, high and low, because of the difference in temperature at the two ends, some current will flow, and that will be measured by a millivolt meter. For example, say this is one conductor, this is another, say copper, this is constantan, this is a hot junction, and this is cold junction. So, this current will flow. Now, if you put a say millivolt meter, this will give a reading, and this millivolt will be proportional to the current, and the current will be proportional to the difference in temperature between the hot and cold junction. So, this is the basic principle. Okay. So, now this is also, this tool and work comprise this tool work thermocouple technique. The work material is a conductive material. The tool is a conductive material, suppose high speed steel or carbide, tungsten carbide, or this is a mild steel, and this is the hot junction. The cutting zone that forms the hot junction, this one. So, the current will flow like this in between, but the job will be mounted in the chuck on insulator. The tool will be mounted on the tool post by insulator, so that the circuit is complete. This circuit is complete. Now, the current will flow along this circuit. This is one tool material, high speed steel, this is a mild steel, another material, and the hot junction. So, current will flow, and that will be recorded in the millivolt meter, and this millivolt recorded will be proportional to the temperature that will develop here. That is maximum temperature that will develop here. Now, this relation between millivolt and this temperature should be developed in advance by calibration. So, if it is 40 millivolt, what is the temperature? Now, this has to be calibrated for these two different materials in advance. How it is done? Here, this is the carbide. Suppose the work material is mild steel, work material is mild steel, this is mild steel, and this is carbide, this is carbide, this is mild steel. Okay. So, this is the junction, and this junction is fitted on a hot plate. Say the copper plate is there, on the copper plate this is brazed. So, when this will be heated, this junction will be also heated, and this is the other cold end, and this is a millivolt meter here, we put a millivolt meter. So, when this will be heated, some millivolt will be generated. Now, what is the temperature here? How shall we know? On the other side, we shall put another thermocouple, standard thermocouple, say chrome enamel thermocouple, and here whenever the same temperature will develop, that will be recorded in the Eurotherm, and from here we can get the temperature. So, what we get from here? On this side we get millivolt, on this side we get temperature, and this is a calibration curve. So, during use, we from any millivolt we can determine what is the cutting temperature. That is called calibration. So, this is a calibration technique which is a must before use of this thermocouple technique. Now, another simple technique is moving thermocouple technique. Moving thermocouple technique. What is it? Suppose we are conducting shaping or planing experiment, and this is the work material moving in this direction with a cutting velocity Vc, and this is the cutting tool, chip flows in this direction. Here a standard thermocouple, say chrome enamel or nickel chrome, is embedded here, okay, braced here, and this is connected to a millivolt meter. Now, when this job will proceed, this layer which is going to be removed is passing through this path, and it first reaches the shear zone, then it goes along the chip. So, when this one is far away from this one, this will not, the temperature is ambient. So, this will not show much reading. When this will come close to the shear zone and passes the shear zone, heat will develop, temperature will rise, that will be indicated here, and the millivolt meter will record. And when this will pass through this, so we get temperature at different point of the path. So, this can be continuously located and recorded. This is called moving thermocouple technique. Next is embedded thermocouple technique. Embedded thermocouple technique. Now, here this is applied for cases where the upper surface is not available for any measurement, okay, directly. Suppose this is grinding or milling cutter or maybe a grinding wheel and finishing the upper surface, all right. Now, we are interested to know the temperature in this region at the grinding zone, all right, how this can be done. First of all, a small hole is made here like this, small hole. Through the hole, a standard thermocouple bit is fitted here. So, this will be close in contact with the job, but there is a gap between, here is a gap. Now, when you conduct the machining work, say Vc, then what will happen? This is Vw, then this will travel in this direction, and this is the direction of travel, okay, and this is the height Hi. Suppose this is at particular Hi. Now, this one, this hole was somewhere here. Now, gradually it will move, come close to this grinding zone and then pass out. So, gradually the temperature will rise in this bit, because when it will be close to the cutting zone where heat is generated, and then it will gradually decrease. So, this temperature recorded here will gradually rise and it will be nearest when close to this one and then gradually go down, but it is not exactly at the same point. This maximum temperature will be when this bead is somewhere here, slightly offset because of the time lag of heat flow. Anyway, so first you take one pass at a particular height Hi and note down what is the maximum temperature observed, theta m. Then you take another pass. When you keep on taking number of passes, this depth of the material gradually decreases. This is Hi, not Hm, Hi. This will gradually decrease. With when this will decrease, this value of theta m will keep on rising. This will keep on rising. So, you measure like this at different values of Hi, but you cannot go to the surface. So, you can go up to say this much. Then to get the surface you extrapolate, just by extrapolation here you get the temperature here. But extrapolation may be difficult in case of say rectangular hyperbola. If you plot in log-log scale, then you get a straight line and you can extrapolate to get the temperature when Hi is very close to 0, very close to 0. That is, you are taking the measurement maximum temperature at the grinding zone. This is a technique, very successful technique, useful technique in grinding, milling, similar operations. Another technique, say compound rake tool. This is compound rake tool. This is the cutting tool. Okay. This cutting tool is made of a non-conducting material. Suppose ceramic. We take ceramic, which is a non-conductor, but it has got a small slit and a hole. This slit is filled up with another tool piece that is made of conducting material, say carbide, tungsten carbide. So, this cutting tool is manufactured by ceramic tool with a small strip of tungsten carbide, which is thermally conductive, at a distance, say L distance, this much. So, what will happen? Say this is Li, this is Li, this distance, and you measure the temperature, the tool work thermocouple technique. This is the hot junction, this is the hot junction at this point, and this is the brush, this is the tool, tool and job, tool work thermocouple technique. So, you are measuring the temperature here. So, temperature is suppose here, this is temperature, okay, temperature I. Now, you now after taking this reading, you just grind this portion, you grind this portion, remove it. So, this value of L will change, it will decrease, you measure temperature again. So, this will rise and this will fall again. That means, you get the temperature along the rake surface, along the rake surface you are getting the temperature profile by this technique. So, it is gradually going high and then gradually decreasing. So, temperature at the center somewhere here, it will be maximum here. So, the temperature distribution along the rake surface can be well measured by this technique. Next is photocell technique. What is photocell technique? This is a photocell. Basically, this is a lead sulfide cell where if light if heat, radiated heat impinges on this sensitive portion of this lead sulfide cell somewhere here, suppose this is the sensitive portion, then its electrical resistance R will change, and this change in electrical resistance, say delta R, this delta R is proportional to the temperature of the source from where heat is radiated and coming and impinging on the surface, say temperature theta, this temperature. Now, in this process a hole is made, but so long the hole is away from the shear zone and this region, there is nothing from where heat is coming. So, there will be no change in this resistance R. Okay. There will be no change in resistance, but when this will move towards in this direction and come into this position, then say here, even here, this hole will be deflected, and from this region heat will be radiated and received by the photocell. By this time this will come to this region, the whole thing is moving in this direction. So, you are getting temperature here, you are getting temperature here. Thus, you can get the temperature all along the shear zone. After that, this hole moves beyond that. So, you get the temperature from this region, temperature from this region. So, heat will be radiated from that flank and you measure that. So, you can get the temperature distribution along the shear plane as well as along the flank surface. So, this is a very nice, reliable and but simple technique of measurement. Next is measurement of temperature, very modern method, advanced technology, very expensive also, measurement of temperature distribution at the tool tip by infrared detection. Infrared detection is a camera where this camera is sensitive to temperature. Depending upon the temperature, some signal will be created in terms of voltage or something, and that by image processing that will be stored in the computer and then displayed in the screen. For example, say this is the cutting tool which has got 3 surfaces. This is the rake surface, this is the if you draw a line of demarcation, then this is auxiliary flank and this is principal flank. Now, if we can make the principal flank exposed to the camera, then the camera can detect the temperature profile like this, these isotherms like this, and on the rake surface also there will be some isotherms. For example, say this is maximum temperature will be here in this region on the rake surface near the tip. So, this is one where the temperature is highest, and the outer periphery the temperature is the lowest. So, the temperature will vary, and this is the isotherms. Entire spectrum of the temperature can be easily and effectively determined and displayed by this infrared technique with the help of a computer. Now, let us see the role of variation of the machining parameters. As I told you that temperature has to be reduced, and that depends upon the process parameters. How do they influence the cutting temperature? We should know, so that we can control the parameters to reduce the temperature. Now, what are the machining parameters? There are different machining parameters. What are those? Work material. What are their specific energy requirement by the material? That is specifically the strength of the material or hardness. Thermal properties, volume specific heat and thermal conductivity. Ductility of the work material. If it is more ductile, more heat will be generated because of intimate contact between the chip and the tool. Then process parameters, most important, cutting velocity, feed and depth of cut. Then tool material, wear resistance. If the tool material wear resistant, then temperature will be less because of less friction. Thermal properties, the thermal conductivity and resistivity. Chemical stability, if it is chemical stable, then less amount of heat will be generated and transferred to the tool, and heat will go towards the chip. Then tool geometry, tool geometrical parameters, rake angle, cutting angle, nose radius and chip breaker if applied. And cutting fluid, very important, what type of cutting fluid you are applying, then what are the properties of the cutting fluid, that is cooling property, lubricating property, viscosity, wetting property and so on, and method of application of the cutting fluid. How do you apply it? Drop by drop, by flood or jet, or as a mist, or from the direction, from top, from bottom, from side and so on. So, all these things play a vital role. Now, the role of machining parameters on the cutting temperature, the general average cutting temperature. This is the average or overall average cutting temperature denoted by theta c. Basically, this is very close to the maximum temperature at the chip tool interface. Lot of experiments have been carried out, lot of analysis have been done, and ultimately an expression like this have been arrived at. It is a very beautiful equation which depicts the role of various parameters on the cutting temperature. What are those? C theta, a constant property of the work material, strength of the work material, cutting velocity to the power 0.4, feed to the power 0.24 and depth of cut 0.105. So, from this equation you find that the variation of velocity plays most important role on theta because its index is 0.4. Next, feed only 0.24 and depth of cut has got minimum effect on temperature because the index is 0.105. Interesting to note that this ratio depth of cut versus feed also plays an important role, significant role on the cutting temperature. Nose radius, that influences the cutting temperature and the product also, but to lesser extent. But there are other parameters also which affect cutting temperature. Those are tool rake angle and inclination angle, because inclination angle affects rake angle and rake angle affects cutting force. Cutting force governs energy, from energy heat is generated, so temperature. Tool clearance angle, if the clearance angle is not there adequately or reasonably, then there will be rubbing action at the work tool interfaces and then there will be lot of heat generation and cutting fluid application. So, the proper application of the cutting fluid, that influences substantially if not remarkably. Now, the control of cutting temperature, how do you control the cutting temperature? So, today we shall just point out what are the methods, and these things will be discussed in detail in the next lecture. Now, anyway, what are the basic approaches of control of cutting temperature? Now, first of all, we should understand what we mean by cutting temperature control. Control of cutting temperature, reduction, the reduction of cutting temperature as far as possible, because it is as such detrimental. How? By proper selection of cutting tools. Now, if we want to reduce the cutting temperature, we should take such cutting tool which produces lesser friction at the chip to interface and heat. Like, say, instead of uncoated carbide, if we take coated carbide tool, then less heat will be generated. If we take ceramic tool high polished, then less temperature will be generated. If we use Sibian cutting tool, less heat will be generated and temperature. Besides that, even if the heat is generated, to reduce the temperature of the tool and the overall, the tool material should be conductive, thermally conductive, then the temperature will decrease to some extent. Next is optimum selection of velocity and feed. In the previous case, we observed that variation of cutting velocity causes more effect or raises the temperature more significantly than increase in feed. Suppose if we increase the velocity, decrease the velocity by 50% and increase the feed by 100%, then the productivity will remain same, the product will remain same, but we can reduce the velocity and increase the feed, then temperature will come down. Of course, the other kind of problems like surface roughness may arise. Then proper selection and application of cutting fluid, which has already been mentioned. For when their temperature is a detrimental fact, then we should apply cutting fluid. Proper application has to be used. Now, if the temperature is very high, then more effective cutting fluid like oil or compound oil, extreme pressure additive type of oil has to be used, which may be expensive, but we have to use it. Then application, in spite of that, if the temperature is not reduced, then we may have to apply special techniques. It has already been mentioned at the beginning of this lecture. There is a technique like hot machining, which softens the work material, as well as the machining force decreases, the energy requirement decreases, heat generation decreases. So, overall temperature may decrease because of this hot machining. Cryo machining, if we apply say cryogen like liquid nitrogen at temperature minus 196 degrees Celsius, then the heat will be absorbed by this, taken away by this cryogen, and temperature will come down. Then dynamic machining, by dynamic machining, which was discussed earlier, the cutting force can be reduced by reducing friction and so on, by more effective cooling, and temperature will come down. So, these are the basic methods of controlling cutting temperature. Now, friend, for your practice there is an exercise, say 2.7, there are two problems given for your practice. Now, problem number 1, what is there? You can easily solve it. The problem 1 states this is for determining J is given, J is known, CV known, and all these things. So you get the value of theta is, putting all these values into this equation, 643 degrees centigrade. So this is the answer. Now this is another problem. This is for the determination of theta I. Here determine theta I, that is average shear zone temperature. You can use the Buckingham formula from dimensional analysis. Q1 is given by this expression, Q2 by this, where Q1 is equal to C1 Q2 to the power n, where n is equal to 0.25 and C1 is a constant. Suppose it is given to a value 121, and there is a material, say A is a machine at such a speed and feed this much under orthogonal turning, and this angle is 90 degree. Determine the interface temperature theta I for the following condition. Lambda is given, rho, this is CV is given, and the ultimate tensile strength 40 kg per millimeter square given. This is percentage elongation 0.2 and zeta 2.5. So these are the values which are given. With the help of these values, you have to determine theta I, this equation. So given solution. Now we are going into the solution. So EC, the specific energy, PZ VC by TSO, the VC is equal to this much. This is specification, you get 500 degrees centigrade. So this is the answer. So this is how you can solve many problems, all right, and you have to practice time to time. So this ends today. Thank you very much.